Welcome to week 4 of our course. This week, our focus shifts to characterizing materials in their hardened state. Just as we related fresh state material characterizations to rheology, we'll now delve deeply into the mechanical behavior of hardened 3D printed concrete materials. Concrete material exhibits significant compressive strength but lacks tensile strength, which is normally necessitating reinforcement with materials like steel to handle the tension within structural elements. Mechanical testing such as a unidirectional compressive strength test or a flexural strength test characterizes the strength. 3D printed concrete undergoes similar mechanical tests, with a crucial difference lying in its orthotropic behavior, displaying varied responses based on loading direction due to weak planes formed during layer deposition. The layer-by-layer technique in 3D printing creates these planes during the interval between the layer depositions, subsequently bonded through hydration and interlocking. That strength referred to as a interlayer bond strength, sometimes shortened term IBS, and the time gap between the layer deposition, that is termed in pause time. The compromised IBS or interlayer bonding strength poses a significant challenge in additive manufactured objects, known as lack of fusion, resulting in reduced mechanical properties due to weak interlayer bonds. While that is actually common in methods like fused deposition modeling, FDM, lack of fusion is prevalent in other methods such as selective laser sintering, selective laser melting, and the powder bed fusion. In extrusion and spray-based concrete printing, lack of fusion occurs between successive filament layers. Differing from traditional FDM or other plastic or steel 3D printing, where it's primarily thermo-induced, lack of fusion in concrete filaments stems from weak hygrochemo interactions or inadequate mechanical surface bonding, interlocking, influenced by the time intervals between the layer depositions, which is the pause time. Whether employing batch mixing or continuous mixing techniques in 3D printed concrete can significantly impact the occurrence of lack of fusion. In batch mixing, the concrete volume needed is mixed separately and transported to the printer or the pump before initiating the 3D printing process. Fresh concrete property evolves over time, resulting in changing behavior from the start to the end of the concrete batch's 3D printing. In contrast, continuous mixing involves feeding freshly mixed concrete to the printer in a continuous mixing printing sequence, maintaining minimal age differences between the printed concrete throughout the 3D printed concrete process. Batch mixing may worsen lack of fusion due to concrete aging before printing, resulting in weaker interlayer strength compared to more robust intralayer strength. This weakness often leads to premature concrete failure, contributing to increased variability in the mechanical properties or hardened 3D printed concrete. Such challenges could impede the widespread adoption of 3D concrete printing in industry, which necessitating consideration for orthotropy and the weakest interlayer regions in structural design. The increased likelihood of crack formation in the typically thin-walled 3D printed concrete structures and the need for reinforcement to achieve the necessary structural integrity add to the technology's reduced cost competitiveness. Lack of fusion, similar to its presence in metal 3D printing, can adversely affect the mechanical performance of printed concrete structures, as I said again. While the intralayer mechanical properties are generally acceptable, the interlayer regions between adjacent filaments exhibit diminished mechanical properties, amplifying with the duration between layer displacement or increased pause time. The decline in strength due to this interlayer effect is represented as a percentage of the weakest mechanical performance of 3D printed specimen compared to reference strength, which is a mold cost specimen. In compression tests, failure occurs along the shear planes that part under compressive triaxial internal stress, extending to the compression tension stress states beyond the triaxial boundary. Weak interlayer bonds prompt crack initiation or propagation, causing filament layers to detach and ultimately leading to premature structural failure. Moreover, individual filament layers might display anisotropy due to material compaction in the extrusion direction caused by the necessary pumping pressure for material transport. Most studies demonstrate a substantial reduction in the mechanical strength of digitally fabricated specimen due to interlayer bonding strength. On average, there is a maximum 45.6% reduction in the mechanical strength of these specimens compared to mold cost points, and with a coefficient of variation of 53.8%. This wide variation poses challenges for design and quality control in the 3D concrete printing industry, raising reproducibility concerns. Interlayer bond strength is influenced by various factors to be elaborated on in the following video. It will vary significantly across printer and material setups, and potentially each project due to the considerable impact of print parameters such as the pause time. Consequently, the severe anisotropic mechanical behavior of printed concrete hinders conforming to conventional norms for reinforced concrete structural design. Detailed load effect assessments examining compression, tension, shear, or flexural behavior in each orientation concerning the specific printer and the material's mechanical capacity become very imperative. This complexity signifies that structural design for 3D printed concrete structures will likely require meticulous or thorough analysis and design time, potentially elaborating costs. Therefore, rectifying lack of fusion in printed concrete becomes crucial for streamlined structural design for such constructions. Concrete, which is normally considered as a durable building material, faces challenges when reinforced with steel due to potential cracks that facilitate corrosion of the reinforcing steel. The corrosion probably occurs via two mechanisms. The first one is a chloride-induced, common in the marine environments or areas treated with de-icing salts. And the second one is carbonation-induced, prevalent in urban spaces with high carbon dioxide levels. Carbonation-induced corrosion generally leads to cracking and spalling of the concrete from the steel, while chloride-induced corrosion is more inclined towards causing pitting and the reduction of the rebar diameter, thus compromising the resistance accordingly. These deterioration mechanisms begin with the ingress of chloride or carbon dioxide ions, often through concrete cracks or regions of high permeability. Concrete with denser microstructures or the use of supplementary cementing materials such as a fly ash and silica fume tends to offer improved durability, achieved through low water to cement ratios or reduced ingress rates via these mechanisms. However, the absence of automated steel inclusion in digitally fabricated elements remains a significant challenge for this burgeoning industry. While post-tensioning or pre-stressing elements have been successfully employed in bridge elements, their uniform geometry might limit the design and the fabrication flexibility offered by digital construction technology, which is normally considered as the biggest benefit of digitally fabricated construction. Recognizing the need for specific reinforcing methods tailored to each 3D printing object, basic reinforcement in longitudinal and vertical direction becomes necessary to ensure ductility post-cracking. Recent studies using X-ray microcomputed tomography, or XCT, examine the microstructure interlayer regions of printed concrete. These investigations reveal that interlayers possess higher permeability compared to intralayers, showcasing a connected micropore network patterns at interlayer regions. Furthermore, research into chloride ingress showed that these interlayer regions may promote earlier corrosion initiation in reinforced steel due to faster ion ingress compared to intralayer regions. These findings indicate that carbonation might cause layer delamination over time, while chloride-induced corrosion might result in pitting at each interlayer region position. The size of filament layers could potentially reduce chloride-induced corrosion in vertically reinforced printed concrete material elements, assuming that interlayer region simulates microcracks due to increased permeability. However, the durability of reinforced 3D printed concrete remains largely unexplored and demands thorough investigation. Modeling multi- or uniaxial reinforced 3D printed concrete elements is recommended to ensure long-term durability. Thank you for your focus. Let's transition to our next session, where we'll delve into the key factors that impact lacquer fusion. I trust that today's session has clarified the concept of interlayer bond strength and the past time and the implications of lacquer fusion. I'll stop the video for now and we'll reconvene shortly. Bye for now.